racing through the earth at a median speed of 30 feet per hour, the auger can drill a 4-foot-wide shaft up to 80 feet deep, all the way down and into the underlying bedrock layer. An impressive feat, considering the machine itself is only 21 feet tall.
Each of these columns, they're designed to go in and sit on the bedrock. The concrete will set up within this column underground, and the skin friction or the resistance of the concrete against the rock is what will hold the bridge up and support the load that the engineers have designed it for.
But up to 25 feet of hard ground lies between them and the bedrock. Crews attach a 48-inch bullet tooth auger bit to the low drill shaft to bore down and gouge the earth out. Invented by the Romans, the auger took a huge step forward around the 14th century with the development of the crank-handled carpenter's brace. The handle is shaped in such a way that holes can be drilled using continuous rotation. Sharp teeth on the front edge of the helix-shaped blade rotate into the wood, and the spiral bit design carries the shavings up the borehole to the surface. Now, supersized and attached to the end of a powerful machine like the low drill, this auger bit can bore dozens of column shafts out of solid ground in a matter of weeks. Spinning at 60 revolutions per minute as the drill descends deeper into the earth, the telescoping drill shaft extends. This is how the low drill can drill a hole almost 3 times its own height. The 35 teeth that line the low drill's auger bit are forged out of tungsten carbide steel. Like teeth in a shark's jaw, the auger's carbide teeth are designed to be replaced if they're damaged or break off while cutting.
We're using 48-inch auger bits with tungsten carbide bits on the end of them. That allows us to chew through smaller rocks, boulders, get down to rock quickly, much faster than the old ways.
Once it strikes bedrock, the crew retracts its auger bit and slides a steel casing tube into the hole to reinforce its unstable dirt walls. The casing tube is 20 feet long and difficult to maneuver over the unstable hole. The low drill attach is designed for boring, not lifting. So here's where it needs some help. Cue the Terex RT555 crane. With a 110-foot-long, dual-winched telescoping boom arm that can lift 55 tons and 4 massive rubber tires, this crane can work in the most treacherous environs, from rocky mountaintops to soggy floodplains. On this job, it works in tandem with the low drill to drop the 20-foot steel casing into the shaft. With the steel casing inserted all the way down to the exposed bedrock, the low drill rolls back into position to finish the job. To get a solid footing for the bridge supports, the crew has to drill a socket 8 to 10 feet into the solid rock, an almost impossible task for the bullet tooth auger. To get this job done, the crew arms the low drill with a 1,200-pound, 48-inch rock core bit, a hardened steel tube edged with tungsten carbide teeth, specifically designed for grinding 4-foot slugs out of solid bedrock very, very slowly.
Well, if the rock real hard, it'll take 1 to 3 days. On average, you should get 1 in every 3 days.
The low drill team is making steady progress drilling and removing huge bedrock slugs. But the most dangerous part of the job is still ahead. When the low drill has finished boring out the hole, crew members will have to inspect the stability of its bedrock base. And there's only one way to do that. Coming up, a brave crew member descends into the dark depths of the bridge column shaft. Work is underway on a massive interstate construction project to widen and reroute a dangerous section of I-40 through downtown Knoxville, Tennessee. The construction team amassed an army of hydraulic excavators to dig, demolish, and drill all over the 4-mile-long job site. In the heart of downtown, Crews are using a low drill attachment on an excavator to bore deep into bedrock, creating 40-foot deep, 4-foot wide shafts into which concrete will be poured to support the columns of a new bridge overpass. But before each hole can be deemed sound enough to support the columns, it needs to be inspected. That job falls to the team geologist, Chris McMichael.
I'm not here to inspect and double check our drilled shafts. We want to test the rock socket and make sure that we're comfortable with the competency of the bedrock and make sure that it meets our design requirements. Most of the rock around here is calcareous or limestone based. We have a lot of solution cavities, a lot of caves and voids, and because of that you can't count on real competent bedrock.
Armed with a rock pick, a small headlamp, and a lot of courage, Chris is lowered into the hole on a makeshift wooden sling. He's checking the bedrock for any large cracks or voids. If he finds any, the crew will have to keep drilling until they reach a more solid rock base. Chris gives the high sign. The shaft and bedrock are fine. The low drill crew now moves on to the next column, while another team preps the hole for concrete. All the water in the bottom of the hole will be forced out by the denser concrete as it fills the hole. Erecting bridges above sea